हाँ जी, नमस्कार, सत श्री अकाल, आदाब। तो अभी हम लोग चैप्टर 9 NCERT क्लास 11 की जो पार्ट सेकंड बुक है उसकी रीडिंग डालने जा रहे हैं। सिर्फ और सिर्फ रीडिंग ही डालेंगे अपन। मतलब शायद समझाने की मेरी काबिलियत नहीं है, लेकिन मैं रीडिंग डालने वाली वीडियो खोज रहा था। कंप्लीट मेरे को नहीं मिल पाई। मैंने सोचा वीडियो बनाऊंगा, मेरा भी काम हो जाएगा और किसी की ज़रूरत भी पूरी हो जाएगी। क्योंकि मैं अकेले पढ़ता हूँ तो पता चलता है 4-5 घंटे और दिन भर में भी एक चैप्टर रीडिंग डाल पाता हूँ। और मैं सिर्फ रीडिंग की बात कर रहा हूँ, मतलब समझ आए ना आए, अंग्रेजी का ज्ञान है तो आपको लगभग मीनिंग तो समझ में आएगा ही। बाकी मीनिंग अपन कर लेंगे, पहले वर्ड्स के साथ तो जान पहचान हो जाए। तो इस तरह की मानसिकता जिनकी है उनके लिए हेल्पफुल हो जाएगी वीडियो। चलिए शुरू करते हैं। चैप्टर 9 मैकेनिकल प्रॉपर्टीज ऑफ सॉलिड्स। 9.1 Introduction. 9.2 Elastic behavior of solids. 9.3 Stress and strain. 9.4 Hooke's law. 9.5 stress strain curve. 9.6 elastic moduli. 9.7 applications of elastic behavior of materials. और फिर उसके बाद समरी, पॉइंट्स टू पॉन्डर, एक्सरसाइज एंड देन एडिशनल एक्सरसाइजेस और हमारा चैप्टर फिनिश। तो आइए शुरू करते हैं। 9.1 इंट्रोडक्शन। इन चैप्टर 7 वी स्टडीड द रोटेशन ऑफ बॉडीज एंड देन रियलाइज दैट द मोशन ऑफ अ बॉडी डिपेंड्स ऑन हाउ मास इज डिस्ट्रीब्यूटेड विद इन द बॉडी। वी restricted ourselves to simpler situations of rigid bodies. A rigid body generally means a hard solid object having a definite shape and size. But in reality, bodies can be stretched, compressed, and bent. Even the appreciably rigid steel bar can be deformed when a sufficiently large external force is applied on it. This means that solid bodies are not perfectly solid. A solid has definite shape and size. In order to change or deform the shape or size of a body, a force is required. If you stretch a helical spring by gently pulling its ends, the length of the string increases slightly. When you leave the ends of the spring, it regains the original size and shape. The property of a body by virtue of which it tends to regain its original size and shape when the applied force is removed is known as elasticity, and the deformation caused is known as elastic deformation. However, if you apply force to a lump of putty or mud, they have no gross tendency to regain their previous shape and get permanently deformed. Such substances are called plastic, and this property is called plasticity. Putty and mud are close to ideal plastics. The elastic behavior of material plays an important role in engineering design. For example, while designing a building, knowledge of elastic properties of materials like steel, concrete, etc. is essential. The same is true in design of bridges, automobiles, ropeways, etc. One could also ask, can we design an aeroplane which is very light but sufficiently strong? Can we design an artificial limb which is lighter but stronger? Why does a railway track has a particular shape like capital I? Why is glass brittle while brass is not? Answers to such questions begin with the study of how relatively small kinds of loads or forces act to deform different solids bodies. In this chapter, we shall study the elastic behavior and mechanical properties of solids, which would answer many such questions. 9.2 Elastic behavior of solids. We know that in a solid, each atom or molecule is surrounded by neighboring atoms or molecules. These are bonded together by interatomic or intermolecular forces and stay in a stable equilibrium position. When a solid is deformed, the atoms and molecules are displaced from their equilibrium positions, causing a change in interatomic or intermolecular distances. When the deforming force is removed, the interatomic forces tend to drive them back to their original positions. Thus, the body regains its original shape and size. The restoring mechanism can be visualized by taking a model of spring ball system shown in figure 9.1. Here the ball represents atoms and spring represent interatomic forces. What is shown in 9.1? Spring ball model for the illustration of elastic behavior of solids. If you try to displace any ball from its equilibrium position, the spring system tries to restore the ball back to its original position. Thus, elastic behavior of solids can be explained in terms of microscopic nature of solid. Robert Hooke, an English physicist 1635 to 703 AD, performed experiments on springs and found that the elongation change in length produced in a body proportional to the applied force or load. In 1676, he presented his laws of elasticity, now called as Hooke's law. We shall study about it in section 9.4. This law, like Boyle's law, is one of the earliest quantitative relationships in science. It is very important to know the behavior of materials under various kinds of loads from the context of engineering design. 9.3 Stress and strain. When a force is applied on a body, it is deformed to a small or large extent depending upon the nature of a material of the body and the magnitude of the deforming force. The deformation may be noticeable visually in many materials, but it is there. When a body is subjected to a deforming force, a restoring force is developed in the body. This restoring force is equal in magnitude but opposite in direction to the applied force. The restoring force per unit area is known as stress. If F is the force applied and A is the area of cross section of the body, magnitude of the stress is equal to F by A. This is equation 9.1. The SI unit of stress is Newton per meter square or Pascal, and its dimensional formula is M per L per T square. There are three ways in which a solid may change its dimensions when an external force acts on it. These are shown in figure 9.2. In figure 9.2 a cylinder is stretched by two equal forces applied normal to its cross-sectional area. The restoring force per unit area in this case is called tensile stress. If the cylinder is compressed under the action of applied forces, the restoring force per unit area is known as compressive stress. Tensile or compressive stress can also be termed as longitudinal stress. In both the cases, there is a change in the length of the cylinder. The change in the length of delta L to the original length L of the body, cylinder in this case, is known as longitudinal strain. Longitudinal stress is equal to delta L by delta L. This is equation 9.2 or formula 9.2. However, if equal and opposite deforming forces are applied parallel to the cross-sectional area of the cylinder, as shown in figure 9.2 ka B, there is relative displacement between the opposite faces of the cylinder. The restoring force per unit area developed due to the applied tangential force is known as tangential or shearing stress. As a result of applied tangential force, there is a relative displacement delta x between opposite faces of the cylinder as shown in figure 9.2 ka B. The strain so produced is known as shearing strain, and it is defined as the ratio of the relative displacement of the faces delta x to the length of the cylinder L. Now shearing strain delta x by L is equal to tan theta. This is our formula number 9.3, where theta is the angular displacement of the cylinder from the vertical original position of the cylinder. Usually usually theta is very small. Tan theta is nearly equal to angle theta in bracket if theta is equal to 10 degree. For example, there is only 1% difference between theta and tan theta. It can also be visualized when a book is pressed with hand and pushed horizontally as shown in figure 9.2 ka C. Thus the shearing strain is equal to tan theta nearly equal to theta. This becomes our equation 9.4. In figure 9.2 ka D, a solid sphere placed is in the fluid under high pressure is compressed uniformly on all sides. The force applied by fluid acts in perpendicular direction at each point of the surface, and the body is said to be under hydraulic compression. This leads to decrease in its volume without any change of its geometrical shape. The body develops internal restoring force that are equal and opposite to the forces applied by the fluid. The body restores its original shape and size when taken out from the solid. Here we had taken fluid now. So the body restores its original shape and size when taken out from the fluid. The internal restoring force per unit area in this case is known as hydraulic stress, and in magnitude is equal to the hydraulic pressure in bracket applied force per unit area. The strain produced by hydraulic pressure is called volume strain and is defined as the ratio of change in volume delta V to the original volume V. Volume strain delta V by V. This is 9.5. Since the strain is a ratio of change in dimension to the original dimension, it has no units or dimensional formula. 9.4. Hooke's law. Stress and strain take different forms in the situations depicted in figure 9.2. For small deformations, the stress and strain are proportional to each other. This is known as Hooke's law. Thus, stress is directly proportional to strain. Stress is equal to K into strain. This is 9.6. Means formula number 9.6. Where K is a proportionality constant is known as modulus of elasticity. Hooke's law is an empirical law and is found to be valid for most materials. However, there are some materials which do not exhibit this linear relationship. 9.5. Stress strain curve. The relation between stress and strain for a given material under tensile stress can be found experimentally. In a standard test of tensile properties, a test cylinder or a wire is stretched by a applied force. The fractional change in length in bracket the strain and the applied force needed to cause the strain are recorded. The applied force is gradually increased in steps and change in length is noted. A graph is plotted between the stress, which is equal in the magnitude to the applied force per unit area, and the strain produced. A typical graph for the metal is shown in figure 9.3. Analogous graphs for compression and shear stress may also be obtained. The stress-strain curves vary from material to material. These curves help us to understand how a given material deforms with increasing loads. From the graph, we can see that in the region between O and A, the curve is linear. In this origin, Hooke's law is obeyed. The body regains its original dimensions when the applied force is removed. In this region, the solids behave as an elastic body. In the region from A to B, stress and strain are not proportional. Nevertheless, the body still returns to its original dimension when the load is removed. The point B is the curve is known as yield point, also known as elastic limit, and the corresponding stress is known as yield strength. sigma y of the material. If the load is increased further, the stress developed exceeds the yield strength and strain increases rapidly even for a small change in the stress. The portion of the curve between B and D shows this. When the load is removed, say at some point C between B and D, the body does not regain its original dimension. In this case, even when the stress is 0, the strain is not 0. The material is said to have a permanent set. The deformation is said to be plastic deformation. The point D on the graph is the ultimate tensile strength, that is sigma u of the material. Beyond this point, additional strain is produced even by a reduced applied force and fracture occurs at point E. If the ultimate strength and fracture points D and E are close, the material is said to be brittle. If they are far apart, the material is said to be ductile. As stated earlier, the stress-strain behavior varies from material to material. For example, rubber can be pulled to several times its original length and still returns to its original shape. Once again, for example, rubber can be pulled to several times its original length and still returns to its original shape. Figure 9.4 shows stress-strain curve for the elastic tissue of the aorta present in the heart. Note that although elastic region is very large, the material does not obey Hooke's law over most of the region. Secondly, there is no well-defined plastic region. Substances like tissue of aorta, rubber, etc. can be stretched to cause large strains are called elastomers. 9.6 Elastic moduli. The proportional region within the elastic limit of the stress-strain curve in bracket region OA in figure 9.3 is of great importance for structural and manufacturing engineering designs. The ratio of stress and strain, called modulus of elasticity, is found to be characteristic of the material. 9.6.1 Young's modulus. Experimental observations show that for a given material, the magnitude of the strain produced is same whether the stress is tensile or compressive. The ratio of tensile or compressive stress sigma to the longitudinal strain, that is cursive E capital, is defined as Young's modulus and is denoted by the symbol y. Y is equal to minus sigma by that capital cursive E. Let me clear from index that what does this capital cursive E pronounced as, means how it is pronounced. Let me clear first. So hello, I got that cursive capital E is pronounced as epsilon. Okay, so now the symbol y is equal to, that represents Young's modulus. Okay, remember that capital Y is equal to minus sigma by epsilon. Okay, this was 9.7, formula number 9.7. From equation 9.1 and 9.2, we have y is equal to f by a by delta L by L. That finally becomes f into L by a into delta L. This is 9.8. Since strain is dimensionless, the unit of Young's modulus is same as that of stress, that is Newton per meter square or Pascal. Table 9.1 gives the values of Young's moduli and yield strengths of some materials. From the data given in table 9.1, it is noticed that for metals, Young's moduli are large, therefore these materials require a large force to produce small change in length. To increase the length of a thin steel wire of 0.1 cm square cross-sectional area by 0.1%, a force of 2000 Newton is required. The force required to produce the same strain in aluminium, brass and copper wires having the same cross-sectional area are 690 Newton, 900 Newton and 1100 Newton respectively. It means that steel is more elastic than copper, brass and aluminium. It is for this reason that steel is preferred in heavy duty machines and structural designs. Wood, bone, concrete and glass have rather small Young's moduli. Example 9.1. A structural steel rod has a radii of 10 mm and length of 0.1 m means meter. 100 kilonewton force stretches it along its length. Calculate A. Stress, B. Elongation and C. Strain on the rod. Young's modulus of structural steel is 2.0 into 10 to the power 11 Newton per meter square. Answer. We assume that the rod is held by a clamped at one end and the force F is applied at the other end parallel to the length of the rod. Then the stress on the board and the rod is given by stress is equal to F by A is equal to F by pi r square. That becomes 100 into 10 to the power 3 Newton by 3.14 into 10 to the power minus 2 meter whole square is equal to 3.18 into 10 to the power 8 Newton per meter square. The elongation delta L is equal to F by AL by Y is equal to 3.18 into 10 का square Newton per meter square by 1 meter by 2 into 10 to the power 11 Newton per meter square is equal to 1.59 into 10 to the power minus 3 meter is equal to 1.59 millimeter. The strain is given by strain is equal to delta L by L is equal to 1.59 into 10 raised minus 9 m by 1 m is equal to 1.59 into 10 raised minus 3 finally becomes 0.16%. Example 9.2. A copper wire of length 2.2 meter and a steel wire of length 1.6 meter, both of diameter 3.0 mm, are connected end to end. When stretched by a load, the net elongation is found to be 0.70 mm. Obtain the load applied. Answer. The copper and steel wires are under a tensile stress because they have the same tension equal to the load W and same area of cross section A. From equation 9.7 we have stress is equal to strain into Young's modulus. Therefore W by A is equal to YC into delta LC by LC is equal to YS into delta LS by LS, where the subscripts C and S refer to copper and stainless strain respectively, or delta LC by delta LS is equal to YS by YC into LC by LS. Given LC is equal to 2.2 m, LS is equal to 1.6 meter. From table 9.1, YC becomes 1.1 into 10 to the power 11 Newton per meter square, and YS is equal to 2.0 into 10 to the power 11 Newton per meter square. Delta LC by delta LS is equal to 2.0 into 10 to the power 11 by 1.1 into 10 to the power 11 into 2.2 by 1.6 is equal to 2.5. The total elongation is given to be delta LC plus delta LS is equal to 7.0 into 10 to the power minus 4 meter. Solving the above equations, delta LC is equal to 5.0 into 10 to the power minus 4 meter and delta LS is equal to 2.0 into 10 to the power minus 4 meter. Therefore, W is equal to A into YC into delta LC by LC is equal to pi 1.5 into 10 to the power minus 3 to the whole square into, in the big bracket, now small bracket starts, 5.0 into 10 to the power minus 4 into 1.1 into 10 to the power 11, small bracket closed, by 2.2, and now the big bracket closes. Finally results into 1.8 into 10 to the power 2 Newton. That's our answer to the question example 9.2. Okay, now example 9.3. In a human pyramid in a circus, the entire weight of the balanced group is supported by legs of a performer who is lying on his back as shown in figure 9.5. The combined mass of all the persons performing the act and the tables, plates, etc. involved is 280 kg. The mass of the performer lying on his back at the bottom of the pyramid is 60 kg. Each thigh bone femur on this performer has a length of 50 cm and an effective radius of 2.0 cm. Determine the amount by which each thigh bone gets compressed under the extra load. Answer: the total mass of all the performers, tables, plates, etc. is equal to 280 kg. Mass of the performer is equal to 60 kg. Mass supported by the legs of the performer at the bottom of the pyramid 280 minus 60 is equal to 220 kg. Weight of the supported mass is equal to 220 kg. Weight is equal to 220 into 9.8 Newton is equal to 2156 Newton. Weight supported by each thigh bone of the performer is equal to half 2156 Newton is equal to 1078 Newton. From table 9.1, the Young's modulus for bone is given by y is equal to 9.4 into 10 raised 9 Newton per meter square. Length of each thigh bone L is equal to 0.5 meter. The radius of the thigh bone is equal to 2 cm. Thus the cross sectional area of the thigh bone A is equal to pi into 2 into 10 raised minus 2 to the whole square meter square is equal to 1.26 into 10 raised minus 3 meter square. Using equation 9.8, the compression in each thigh bone in bracket delta L can be computed as delta L equals to F into L by Y into A is equal to 1078 into 0.5 pi 9.4 into 10 to the power 9 multiplied by 1.26 multiplied by 10 to the power minus 3, that finally equals to 4.55 into 10 to the power minus 5 meter or 4.55 into 10 to the power minus 3 centimeter. This was our answer. This is very small change. The fractional decrease in the thigh bone is delta L by L is equal to 0.000091 or 0.0091%. Now moving to the next section, 9.6.2. Determination of Young's modulus of the material of a wire. A typical experiment arrangement to determine the Young's modulus of a material of wire under tension is shown in figure 9.6. It consists of two long straight wires of same length and equal radius suspended side by side from a fixed rigid support. The wire A, called the reference wire, carries a millimeter main scale M and a pan to place a weight. The wire B, in bracket called the experimental wire, of uniform area of cross section, also carries a pan in which known weights can be placed. A vernier scale V is attached to a pointer at the bottom of the experimental wire B, and main scale M is fixed to the reference wire A. The weights placed in the pan exert a downward force and stretch the experimental wire under a tensile stress. The elongation of the wire increase in length is measured by the vernier arrangement. The reference wire is used to compensate for any change in length that may occur due to change in room temperature. Since any change in length of the reference wire due to temperature change will be accompanied by a equal change in experimental wire, in bracket we shall study this temperature effects in detail in chapter 11. Both the reference and experimental wires are given an initial small load to keep the wires straight and vernier reading is noted. Now the experimental wire is gradually loaded with more weights to bring it under a tensile stress, and the vernier reading noted again. The difference between two vernier readings gives the elongation produced in the wire. Let R and L be the initial radius and length of the experimental wire respectively. The area of cross section of the wire would be pi r square. Let M be the mass that produces an elongation delta L in the wire. Thus the applied force is equal to mg, where g is the acceleration due to the gravity. From equation 9.8, what was that? The equation 9.8 was the equation 9.8 was y is equal to F into L by A into delta L. Okay, so here from equation 9.8, the Young's modulus of the material of the experimental wire is given by y is equal to sigma by epsilon is equal to mg by pi r square into L by delta L is equal to mg into L by pi r square into delta L, and this becomes our next 9.9 formula number. Moving to the next section, 9.6.3, shear modulus. The ratio of shearing stress to the corresponding shearing stress is known as, I pronounced some different. Once again, the ratio of the shearing strain is called the shear modulus of the material and is represented by G. It is called the modulus of rigidity. G is equal to shearing stress sigma s by shearing strain. G is equal to F by A by delta x by L is equal to F into L by A into delta x. This is 9.10 equation number. Similarly, from equation 9.4, G is equal to F by A by theta is equal to F by A into theta. The shearing stress sigma s can also be expressed as sigma s is equal to G into theta. This is equation number 9.12. SI unit of shear modulus is Newton per meter square or Pascal. The shear moduli of a few common materials are given in table 9.2. It can also be seen that the shear modulus or modulus of rigidity is generally less than Young's modulus. from table 9.1. Okay, for most materials G is approximately equal to Y by 3. Let's move to example 9.4. A square lead slab of side 50 cm and thickness 10 cm is subject to a shearing force in bracket on its narrow face of 9.0 into 10 to the power 4 Newton. The lower edge is riveted to the floor. How much will the upper edge be displaced? Answer. The lead slab is fixed and the force is applied parallel to the narrow face as shown in figure 9.7. The area of the face parallel to which the force is applied is A is equal to 50 cm into 10 cm is equal to 0.5 meter into 0.1 meter is equal to 0.05 meter square. Therefore, the stress applied is 9.4 into 10 raised 4 Newton by 0.05 meter square. That becomes 1.80 into 10 to the power 6 Newton meter per square. Newton per meter square. Okay. We know that shearing strain is equal to delta x by L is equal to stress by G. Therefore, the displacement delta x is equal to stress into L by G is equal to 1.8 into 10 raised 6 Newton per meter square into 0.5 meter by 5.6 into 10 raised 9 Newton per meter square, and that finally gives us the answer 1.6 into 10 to the power minus 4 meter is equal to 0.16 mm. Let's move to the next section, 9.6.4 bulk modulus. In section 9.3 we have seen that when a body is submerged in a liquid, or broadly say it fluid, it undergoes a hydraulic stress in bracket equal in magnitude to the hydraulic pressure. This leads to decrease in the volume of the body, thus producing a strain called volume strain. Equation 9.5. The ratio of hydraulic stress to the corresponding hydraulic strain is called bulk modulus. It is denoted by symbol B. B is equal to minus P by delta V by V. This is our 9.13 equation number. The negative sign indicates the fact that with an increase in pressure, a decrease in volume occurs. That is, if P is positive, delta V is negative. Thus, for a system in equilibrium, the value of bulk modulus B is always positive. SI unit of bulk modulus is the same as that of pressure, that is Newton per meter square or Pascal. The bulk moduli of a few common materials are given in table 9.3. The reciprocal of the bulk modulus is called compressibility and is denoted by K. It is defined as the fractional change in volume per unit increase in pressure. K is equal to 1 by B is equal to minus 1 by delta P into delta V by V. This is our equation number 9.14. It can be seen from the table in which data is given, and that is our table number 9.3, that the bulk moduli for solids are much larger than for solids, which are again much larger than the bulk modulus for gases in bracket air. So table number 9.4 indicates, lists or shows bulk moduli in bracket B of some common materials like aluminium, brass, copper, glass, iron, nickel, steel, and in liquids water, ethanol, carbon disulfide, glycerin, mercury, and then gases at STP, and their bulk moduli in the order of 10 to the power 9 Newton per meter square, or let's say GPa, is given as for aluminium 72, brass 61, and 140, 3700, 260, 160, and like that for liquids like water 2.2, ethanol 0.9, and then 1.56, 4.76, 25, and at last for gases like air 1.0 into 10 to the power minus 4. So these were the values for the materials, solids, liquids and gases. Thus, solids are least compressible, whereas gases are the most compressible. Gases are about 1,000,000 times more compressible than solids. Wow! Gases are about 1,000,000 times more compressible than solids. Great difference. Gases have large compressibilities which vary with pressure and temperature. The incompressibility of the solids is primarily due to the tight coupling between the neighboring atoms. The molecules in liquids are also bound with their neighbors but not as strong as in solids. Molecules in gases are very poorly coupled to their neighbors. Table 9.4 shows the various types of stress, strain, elastic moduli, and the applicable state of matter at a glance. Example 9.5. The average depth of the Indian Ocean is about 3000 meter. Calculate the fractional compression. Delta V by V of the water at the bottom of the ocean, given that the bulk modulus of the water is 2.2 into 10 raised 9 Newton per meter square. Take G is equal to 10 meter per second square. Solution. The pressure exerted by a 3000 meter column of water on the bottom layer, P is equal to H rho G is equal to 3000 meter into 1000 kg per meter cube into 10 meter per second square, finally becomes 3 into 10 to the power 7 kg per meter per second square is equal to 3 into 10 to the power 7 Newton per meter square. Fractional compression delta V by V is delta V by V is equal to stress by B is equal to 3 into 10 to the power 7 Newton per meter square by 2.2 into 10 raised 9 Newton per meter square is equal to 1.36 into 10 raised minus 2 or 1.36%. So this is our answer. Again here table 9.4 shows stress, strain and various elastic moduli. For example, types of stress like tensile or compressive, shearing or hydraulic, okay, and then stress, strain, change in shape, volume, elastic modulus, name of modulus, state of matter for the respective types of stress are listed. Now let's move on the next second last section 9.7, and then at last, after discussing summary and points to ponder, our chapter is finished, or you may say this is the last section, and only then summary and points to ponder will remain. So 5 or 7 minutes more, just hold down. Applications of elastic behavior of materials. The elastic behavior of materials play an important role in everyday life. All engineering designs require precise knowledge of the elastic behavior of materials. For example, while designing a building, the structural design of the columns, beams and supports require knowledge of strength of materials used. Have you ever thought why the beams used in construction of bridges as supports etc. have a cross section of the type I? Why does a heap of sand or a hill have a pyramidal shape? Answer to these questions can be obtained from the study of structural engineering, which is based on the concepts developed here. Cranes used for lifting and moving heavy loads from one place to another have a thick metal rope to which the load is attached. The rope is pulled up by using pulleys and motors. Suppose we want to make a crane which has a lifting capacity of 10 tons or metric tons. 1 metric ton is equal to 1000 kg. How thick should a steel rope be? We obviously want that the load does not deform the rope permanently. Therefore, the extension should not exceed the elastic limit. From table 9.1 we find that milled steel has a yield strength SY of about 300 into 10 raised 6 Newton per meter square. Thus the area of cross section A of the rope should be at least A greater than or equal to W by SY is equal to mg by SY. This is our equation number 9.15 is equal to 10 to the power 4 kg into 10 meter per second square by 300 into 10 raised 6 Newton per meter square, and finally it gives 3.3 into 10 raised minus 4 meter square, corresponding to the radius of about 1 centimeter for a rope of circular cross section. Generally, a large margin of safety in bracket of about a factor of 10 in the load is provided. Thus a thicker rope of radius about 3 cm is recommended. A single wire of this radius would practically be a rigid rod, so the ropes are always made of a number of thin wires braided together like a pigtails for ease in manufacture, flexibility and strength. A bridge has to be designed such that it can withstand with the load of the following traffic: the force of winds and its own weight. Similarly, in the design of buildings, use of beams and columns is very common. In both the cases, the overcoming of the problem of bending of beam under a load is of primary importance. The beam should not bend too much or break. Let us consider the case of a beam loaded at the center and supported near its ends as shown in figure 9.8. A bar of length L, breadth B and depth D, when loaded at the center by a load W, sags by an amount given by delta is equal to W liter L W LQ. Once again, delta equal to WLQ by 4 BDQY. This becomes our equation number 9.16. This relation is derived using what you have already learnt and little calculus. From equation 9.16 we see that to reduce the bending for a given load, one should use a material with a large Young's modulus Y. For a given material, increasing the depth D rather than the breadth B is more effective in reducing the bending. Since delta is proportional to D to the power minus Q and only to B to the power minus 1, in bracket of course of length L and span should be as small as possible. But on increasing the depth, unless the load is exactly at the right plane, in bracket difficult to arrange in a bridge with moving traffic, the deep bar may bend as shown in figure 9.9 to the B. This is called buckling. To avoid this, a common compromise is the cross-sectional shape shown in figure 9.9 to the C. This section provides a large load-bearing surface and enough depth to prevent bending. This shape reduces the weight of the beam without sacrificing the strength and hence reduces cost. Use of pillars or columns is very common in buildings and bridges. A pillar with rounded ends as shown in figure 9.10 ka A supports less load than that with a distributed shape at the ends, which is shown in figure 9.10 ka B. The precise design of a bridge or a building has to take into account the conditions under which it will function, the cost and long period, reliability of usable materials, etc. The answer to the question why the maximum height of a mountain on earth is approximately 10 km can also be provided by considering the elastic properties of rocks. A mountain base is not under uniform compression, and this provides some shearing stress to the rocks under which they can flow. The stress due to all material on the top should be less than the critical shearing stress at which the rocks flow. At the bottom of the mountain of height h, the force per unit area due to the weight of the mountain is h rho g, where rho is the density of the material of the mountain and g is the acceleration due to gravity. The material at the bottom experiences this force in the vertical direction and the sides of the mountain are free. Therefore, this is not a case of pressure or bulk compression. There is a shear component approximately h rho g itself. Now the elastic limit for a typical rock is 30 into 10 raised 7 Newton per meter square. Equating this to h rho g with rho is equal to 3 into 10 raised 3 kg per meter cube gives h rho g is equal to 30 into 10 raised 7 Newton per meter square, or h equals to 30 into 10 to the power 7 Newton per meter square by 3 into 10 raised 3 kilogram per meter cube into 10 meter per second square. Finally gives result as is equal to 10 kilometer, which is more than the height of Mount Everest. Really. So we have completed the chapter. Now let's move to summary. First point: stress is the restoring force per unit area and strain is the fractional change in the dimension. In general, there are three types of stresses. A. Tensile stress, longitudinal stress associated with stretching or compressive stress associated with compression. B. Shearing stress, and C. Hydraulic stress. Second, for small deformations, stress is directly proportional to the strain of many materials. This is known as Hooke's law. The constant of proportionality is called modulus of elasticity. Three elastic moduli, viz. Young's modulus, shear modulus, and bulk modulus, are used to describe the elastic behavior of objects as they respond to deforming forces that act on them. A class of solids called elastomers does not obey Hooke's law. Third number, when a object is under tension or compression, the Hooke's law takes the form F by A is equal to Y delta L by L, where delta L by L is the tensile or compressive strain of the object. F is the magnitude of the applied force causing the strain. A is the cross-sectional area over which F is applied perpendicular to A, and Y is the Young's modulus for the object. The stress is F by A. Fourth point, the pair of forces when applied parallel to the upper and lower faces, the solid deforms so that the upper face moves sideways with respect to the lower. The horizontal displacement delta L of the upper face is perpendicular to the vertical height L. This type of deformation is called shear, and the corresponding stress is the shearing stress. This type of stress is possible only in solids. In this kind of deformation, the Hooke's law takes the form F by A is equal to G into delta L by L, where delta L is the displacement of one end of object in the direction of the applied force F, and G is the shear modulus. Fifth and the last one. When an object undergoes hydraulic compression due to a stress extended by a surrounding fluid, the Hooke's law takes the form P is equal to B into delta V by V, where P is the pressure in bracket hydraulic stress on the object due to the fluid, and delta V by V, which is the volume strain, is the absolute fractional change in the object's volume due to that pressure, and B is the bulk modulus of the object. We have completed summary also, and now the last part of this reading is points to ponder. Let's ponder into the points. Okay, 2-3 minutes more. Just wait, please. 2-3 points. 2-3 minutes more only. First, in the case of a wire suspended from ceiling and stretched under the action of a weight in bracket F suspended from its other end, the force exerted by the ceiling on it is equal and opposite to the weight. However, the tension at any cross section A of the wire is just F and not 2F. Hence, tensile stress, which is equal to the tension per unit area, is equal to F by A. Second, Hooke's law is valid only in linear part of the stress strain curve. 3. The Young's modulus and shear modulus are relevant only for solids, since only solids have lengths and shapes. Fourth, bulk modulus is relevant for solids, liquids and gases. It refers to the change in volume when every part of the body is under the uniform stress so that the shape of the body remains unchanged. Fifth, metals have larger values of Young's modulus than alloys and elastomers. A material with large value of Young's modulus requires a large force to produce small changes in its length. Sixth, in daily life, we feel that a material which stretches more is more elastic, but it is a misnomer. In fact, material which stretches to a lesser extent for a given load is considered to be more elastic. Seventh, in general, a deforming force in one direction can produce strains in other directions also. The proportionality between stress and strain in such situations cannot be described by just one elastic constant. For example, for a wire under longitudinal strain, the lateral dimensions in bracket radius of cross section will undergo a small change, which is described by another elastic constant of the material called Poisson ratio. Eighth and the last one, stress is not a vector quantity, since unlike a force, the stress cannot be assigned a specific direction. Force acting on the portion of a body on a specified side of a section had a definite direction. So we have completed the chapter. Best of luck for your understanding. Have a good day. Bye bye. Let's meet on the next chapter. Till then, take care and be happy. Keep smiling, because smiling does not charge anything. Okay, take care of yours, family and your dear ones. Okay, bye bye.